In question 1, it is important to sort out the variables and understand the relationships between alleles, genotypes, and frequencies. We have a population of N people with 2 N chromosomes each. The 3 genotypes are homozygous big A, heterozygous big A, and homozygous a. Big A has a frequency of P, big A has a frequency of Q, and a has a frequency of R. The big A allele has frequency P, and the little a allele has frequency Q. The equation to find frequency P is big P plus 1/2 of big Q. This equation makes sense because big P contains both big A alleles, while big Q is only 1/2 of the big A allele. Using this equation, we can find the frequency of big A. Applying the same reasoning, you can determine the equation to find the frequency of Q as shown. In question 2, we simply use the data given and plug the values into the equations above. To find the frequency of the big A allele, we plugged in 0.8 for P and found the frequency to be 1.3. Additionally, we plugged in 0.2 for R and found the frequency of the little a allele to be 0.7. We knew that the total yield had to be 1, but in this case, they added up to 2. Because of this, we knew to divide each equation by 2. Therefore, the frequency of the big A allele is 0.65 and the frequency of the little a allele is 0.35. In combination, these frequencies add up to 1.
In Part A of Question 3, our aim is to prove that our given balanced equation of f of p equals 0.8 p squared plus 1 times 2 pq plus 0.2 q squared is equal to the equation f of p equals 1 minus 0.2 p squared minus 0.8 open parentheses 1 minus p close parentheses squared. There are 2 ways in which we can prove the equations equal each other. The first way is to combine our p and q equations from number 2. By combining the 2 equations, we get f of p equals negative p squared plus 1.6p plus 0.2. Next, we can break up our negative p squared into negative 0.2p squared and negative 0.8p squared, and 0.2 into 1 and negative 0.8. From here, we can factor out our open parentheses 1 minus p close parentheses squared from the last 3 terms. By doing this, we achieved our goal by getting the equation f of p equals 1 minus 0.2p squared minus 0.8 open parentheses 1 minus p close parentheses squared. The other way in which we can prove the equations equal each other is by simply plugging in the p and q values that we got from 2 into both equations. When we do this, both sides equal 0.8175. In Part B of Question 3, our goal is to find the value p that maximizes f of p. To do this, we took the derivative of the original equation f of p equals 0.8 p squared plus 1 times 2p cubed plus 0.2 q squared. To get the derivative equation, f prime of p equals negative 0.4p plus 1.6 minus 1.6p. Finally, we solved for p in the derivative equation and found that the max of p is 0.8. When you plug the 0.8 back into the equation, you find that f of p equals 0.84.
In this question, we are given the general probabilities of mating. Big A has a probability of 1 plus s sub 1, which is greater than or equal to 0. Big A has a probability of 1. Little a has the probability of 1 plus s sub 2, which is greater than or equal to 0. Additionally, we are given the equation of f of p as shown in green. To find where the maximum occurs, we took the derivative of the f of p function and set it equal to 0. We found that the maximum occurs when p hat equals s sub 2 divided by the quantity of s sub 1 plus s sub 2. The derivative calculations are shown below in blue. From here, we used the given probabilities and the frequencies from question 2 and found that s sub 1 equals negative 0.2 and s sub 2 equals negative 0.8, as seen in the work in purple. Next, we plugged in the s sub 1 and s sub 2 values into our equation for p hat to find that p hat equals 0.8. To prove that we have a maximum, we performed the first derivative test by plugging in -0.5 and 1 into the derivative of f of p. We see that the function of the first derivative goes from increasing to decreasing, which confirms that we did solve for a maximum. Lastly, we proved that f of p hat equals 1 plus the quantity of s sub 1 times s sub 2 divided by the quantity of s sub 1 plus s sub 2 is less than 1. We found f of p hat equaled 0.84, which is less than 1.
In the last problem, we are trying to find the frequency of the big A alleles of the adults in the next generation. We can use the frequencies of the alleles we found in problem 2 to predict these future frequencies. The allele frequencies from the first generation are now labeled P0 for big A. The frequency for big A can be determined by P0 squared. Since P0 equals 0.65, P0 squared equals 0.4225. We determined S sub 1 in the last section to equal -0.2. In order to determine P sub 1, we can use an equation that was provided. Since f of P0 is in the denominator of the equation to find P sub 1, we solved for that first using a given equation from section 3 and plugged in the P0 and P0 squared values from above. After doing the calculations as shown, we found f of P0 to be 0.8175. Subbing in the numbers we determined previously for s sub 1, P0, and P0 squared, we can fill in the numerator of this equation. We can plug 0.8175 into our denominator. After doing the work, we determined the frequency of big A in the adult population to be 0.69174.
And this concludes our presentation on optimization and genetics.